All right. So, hello everyone. Forgot to record this, so it'll just be me kind of doing a quick recap of what I did in day one for this kind of electrochemistry modeling workshop. So, the first thing I talked about was, um, oops. The first thing I talked about was the electrochemical cell. Right, and so for us battery folks, this typically looks like you have two electrodes, positive and negative, and they'll be connected up to um, a load or a potentiostat, right? That'll connect the two electrodes. Some people doing more analytical stuff might have, a beaker or some type of electrochemical cell. And they'll have some negative electrode and some positive electrode that'll sit inside of it. Um, and they'll be connected to this load slash potentiostat, right? And so, typical of things that we think about trying to understand are what would be the voltage between the positive and negative, right? And we also want to know what would be the current flowing from the positive to negative electrode. So V and I are very important parameters. So we have a few parameters that just variables in the system that we want to understand. And right now we have voltage, we have current. Some other ones that we might think about are power, which is voltage times current. And this is instantaneous, and so it'll change throughout time, right? So keep that in mind. Um, you can, you might also care about the energy density, or maybe let's just look at the energy for now. So the energy is going to be equal to the integral of the power with time, based on the bounds that you care about. And so, and this is from the fact that power, the definition of it is the change in energy with time. And so we can put in this first result in here, so we can say the energy, so this one was power, right? This one was energy of this energy released or put into the system, right? Is we could say this is voltage times current, integral of dt. But so knowing that the amount of charge that you get out, and we'll just say it's a differential, but you could just as easily say delta Q in this case is equal to I, like dt or delta t, right? So it doesn't matter how small of a charge or how small of a time. So we know that the energy now is equal to the integral of the voltage with the charge. So if you had some plot of voltage versus charge that say looked like this, right, you get the energy by integrating this curve. If you had the kind of the average, if you had the average voltage in this case on this plot, then you could also pull this out, and so E could also be equal to V average times Q total, right? Where in this case, this would be like probably V average, and this point here would be Q total, right? So you could also kind of just lump that into kind of a rectangle. So those are some other parameters that we're gonna care about when we're trying to model our systems. We're going to be tracking voltages and currents, and that's going to help us track also powers and energy that we're getting out of our system. And you can see why those are important. And you'll also see that the voltage especially is related to a lot of thermodynamic and chemical properties of the system that you might also, for analytical folks, might be more interested in knowing. So kind of the typical process for modeling, and there's a lot of different ones, but let's just say kind of at a high level what's usually done, especially in the models we're going to use, which are, you know, generally kind of continuum models. We're not tracking individual particles. What you're typically going to do is fix the current in the system. So you're going to use that as a boundary condition, and then you might track all the mobile species as they move. We're not going to do this to start because it requires a little bit of a more microscopic view into the system to be able to track some of these. So we're going to look at it at a little bit higher level to start and then get into that portion of it. And then 3, we're going to calculate the voltage. And then we'll be, and this could be transient or not transient, like it could be steady state or transient. So you could run this model and say, oh, this is how the voltage is going to change with time at that current, or you could just say this is the voltage and current for this condition at steady state. So both those are done, and then usually we'll repeat it for different currents. And look how that changes. It changes your power, energy. So this is that's the typical process. And so I want to look at and you can see that, you know, so if the current's fixed, that one of the important things, I'm going to save tracking the mole species. I'm going to focus more on this since that's useful also at a high level. How do you know what the voltage is? So let's talk a little bit about cell voltage and modeling the cell voltage. Okay, so let's look at a specific system. I want to look at a fuel cell, and more specifically a PEM fuel cell. So that stands for proton exchange membrane. So they're kind of a low temp membrane that exchanges protons. Some people call them polymer electrolyte membranes, fuel cells. So they have at the core is this membrane, which is a proton conductor, electron insulator. So this thing is like a fluorinated polymer that has water in it. Then you're going to have 2 similar layers. So these are our catalyst layers. So catalyst plus gas diffusion layer. And then you're going to have your channels. So I have this. And I'm going to call this the negative, this the positive. And so what you're going to have coming in to this system is hydrogen and oxygen. And what's going to be coming out is water. Right? And it's a half a molecule of oxygen. Maybe it's better to think about a half mole of oxygen to get the stoichiometry correct. So the reactions occur in this catalyst and then in the gas diffusion layer. So that allows those gases to diffuse to the catalyst. And then you'll have your load connected between these two. So this is your load for your potentiostat, right? Current is positive going this way. So charge, that's a charging current. Or sorry, discharging current. Um, so what do I want to say next? Okay, so in this case, we notice we're transferring hydrogen from the negative side over to the positive side, and we're getting 1.2 volts from the system. Um, and the way that's done is that the membrane in the middle, so it doesn't allow it doesn't conduct, the hydrogen atom. It doesn't conduct electrons, just the proton. So, but this extra circuit allows the electrons to flow. So around here, you have your electrons flowing. And so what we can say is what must be is our so first I should first write the full reaction. So the full reaction is this hydrogen plus oxygen turning into water, right? And so in half reactions, we're going to split this into two half reactions on each side. So in electrochemistry in general, you're going to have half reactions, or at least what we call half reactions, because by kind of their very nature, we're going to split the redox reaction to occurring in two different locations in the cell on the surface of the electrodes. So electrochemical systems. Electrochemical systems split. Separated in space, and they happen on an electrode surface, so they're homogeneous, or sorry, heterogeneous kind of by nature. They're on a surface, they're not happening in the bulk. So our negative reaction, we said, okay, well, we need our hydrogen has to split into two protons and two electrons so that it can get to the other side of the cell, the positive side of the cell, which is where we have our oxygen. Plus we're going to get these protons, plus we're going to get these electrons, and we're going to form water. Right, and so you can see what's happening is originally both these molecules, this is neutral, and this is neutral. But you can see since this is just just hydrogen, it's going to equally pull it. So they're both going to have kind of an oxidation state of 0. Same thing with the oxygen, but here oxygen is more electronegative than hydrogen, so it's going to pull the two electrons that it wants, one from each of these protons. And so you can see the redox reaction is kind of the transfer of electrons from the hydrogen to the oxygen, and it's been split up into two locations in the cell. So we're still thinking about voltages, right? So the voltages of these two reactions don't really mean anything. That's a reference reaction. And so it's kind of like saying, all right, you have a ball on a hill, right? And saying, okay, well, and someone tells you what the potential energy is. It's like, well, that potential energy doesn't really mean anything unless you know what the reference height is, right? So is this, is this the reference where potential energy equals 0? Or is this? Or is like down here, right? So unless you, so similar voltages are like that. So if you talk about the voltage of this half reaction, it doesn't really mean anything unless it's referenced to another half reaction. luckily, this reaction here is the most common reaction we reference the other half reactions too. So we'll kind of see how that comes into play. So, and before we get into voltages, I need to talk a little bit about chemistry, right? And so we typically, for these reactions, we think about the change in Gibbs free energy. Gibbs free energy. And it's equal to both the change in enthalpy minus the product of temperature and entropy. And that's absolute temperature. And so this is the work that can be done by a system that pressure and temperature equals a constant, so constant pressure and temperature. This is work that can be done by system at constant pressure, right? So that's used a lot for combustion and getting heat off of combustion reactions. Of course, those systems are also limited by Carnot and the second law of thermodynamics, but this is kind of the max. Let's say you had infinitely hot systems, they could approach this. Entropy, this is how likely are you to get that system, how likely. Right, and so you have kind of more of like an energy term associated with the Gibbs free energy that's what we're looking for and we're always thinking about in electrochemistry, and more of a probability term. So both of these determine together the outcome, and depending on the temperature, the relative influence on the outcome can be changed. So I think kind of thinking about, well, what the heck do you mean by probability, Chris? So let's say I'm a mechanical engineer, so I like to think about balls and hills. So sorry if you have maybe this isn't your leaning, but so let's say we have our 3 balls, right? And so this is obviously higher in energy, so this is not likely for that to, if you shook the thing up and find all the balls there. This is lower in energy, maybe you'd find all 9 balls down here at the bottom. But it's also not that likely because they're not all spread out, right? And so what's maybe more likely is you'd find something like this. Right? So this is lower in energy, right? But it's actually higher, but it's also it's lower probability that you have this because everything is all clustered together. That's probably unlikely that you'd see the system. And this is going to be your most likely outcome because it's lower in energy, plus it's highly probable. Right? So you see how you can't just use energy to predict, what's the state of your system, right? And so this is what you're going to find it in. So that's the importance of keeping the entropic term in there. So and the Gibbs free energy, not only, so if you could capture the let me just say this. So the Gibbs free energy, it depends on the conditions of your system as well. So this is like, right, so it depends on, we call this the activities of the reactants. products. So the reactants and the products. And so activities we usually model, or we usually relate those to pressures, concentrations. Right, so that's how we'll usually model those. Um, so what we'll typically do is, because we don't want to tabulate, we don't want to like figure out what these enthalpy and entropies are under all different conditions. We'll typically say, okay, well, the Gibbs free energy, and the lowercase is usually on a per mole basis, is per mole, it's lowercase, is going to be equal to some Gibbs free energy at standard temperatures and pressures and other conditions, right? Obviously we have concentrations in there, right? Plus we'll have a term, this RT, RT natural log of what we're going to have here is we're going to have a term that helps capture some of the changes in the entropic terms for these different conditions for activities. And so if it's since we're going to look at a lot of systems where they're kind of like, you have dissolve active species, we're going to look at concentration. So you have concentrations of your products divided by some standard concentration. This will be to the power of the kind of coefficient. So if you did like a chemical reaction like this, for the whole reaction, you'd have a half in front of the oxygen terms, or this would be like to power of a half. So keep that in mind, that those terms will come in to being powers. Over, we have the concentration of our reactants at standard and times those. But you could, let's say you're doing a system that was not, it wasn't a dissolved system or kind of a liquid-based system, it was gaseous, then you'd use pressure. So you could use pressure for gaseous systems. And so you'll see that. And so standard conditions for like pressures, 1 bar. For concentrations, it's 1 molar. I've seen some old texts say it's one molal, the like per kilogram. I'd actually I didn't see that before whenever I was learning it. Be interesting to see, but as far as I can tell, everyone uses 1 molar. I mean, most of the time the terms cancel out, so it doesn't have, usually these terms and these terms will cancel out, but they don't always cancel out. So it does have an effect. So and if we look at like kind of the Gibbs free energy of the system as you go from hydrogen and oxygen going over to water on this side, you'll find that there's some, it's going to be highly, over on this side for kind of our reaction in the system. And this is and so if your system's like here, that means it's going to run this way, which means that you're going to have this forward reaction. So we're going to say we're going to have this forward reaction. If your system's, maybe over here, you're going to have this backwards reaction, right? And so that's going to be the backwards reaction, right? And then if you're at equilibrium, which might be like here, so equilibrium, then you have forward and backwards are equal. Right, and so it's going back and forth. You've reached a kind of equilibrium condition. So we're going to first analyze kind of conditions where this is under equilibrium. And so in both these cases, delta G is negative, right? So it's going to a lower so if this is delta G, it's going to a lower Gibbs free energy in both of these cases, right? So these are both of these cases, delta G less than 0 is spontaneous, right? Release energy. Delta G greater than 0, this is like non-spontaneous, right? So we're still getting up to this question about the voltage in these systems. So if you knew, so and this is just kind of a chemical viewpoint. So if we want to include kind of the electrochemical aspects, I keep doing that. Electrochemical. And what we're going to do is we're going to define the electrochemical Gibbs free energy. So Econ Gibbs. And what we're going to do is we're going to take, I'll just use the deltas for now, because we're going to take our normal Gibbs free energy and we're going to add in a term NFE. And this is the charge in the half reaction. And they should be the same in both, otherwise the system won't cancel. This is Faraday's constant. Which is going to be 9,640, 485 coulombs per mole of fundamental charges, so like electrons or protons. And this E is voltage. Right? And so if we say, okay, well, a system, so Echem in equilibrium, right? So we're going to basically say that our change in Gibbs free energy must be 0 for the reaction. It must be in equilibrium, so it must be equal forward and back. So our E, when we solve for this, we're going to get a negative delta G naught, right? So I'm going to put both terms. So you have this G naught term, right? And then you're going to have this RT dot 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 term. So minus G naught at standard conditions over NF. And then you're going to have minus RT over NF, natural log of concentration of your products over the concentration of your reactants. And this is, let's just say A equals B equals 1 in this case. Just, you can, I hope you've seen enough of these, equilibrium constants, and I've dealt enough with these that you kind of, know what that term is. But, roughly you have a term representing the kind of the activities or concentrations of your products over your reactants. And so we'll typically say this is your voltage is equal to your standard reduction potential, which is this E naught here. And usually we'll bring this minus sign here, up here, into here. So you can bring it up into a power. So that's a property of logs or natural logs. So we have plus RT over NF, natural log of your reactants over your products. And so you see here that if you increase the concentration of your reactants, then your voltage goes up, which should jive. And so you can basically see, to get our voltage, we need to know the change in enthalpy, change in entropy. We need to know the temperature, concentration of our reactants, and concentration of our products. So this is all stuff that we're going to need to know. So let's start by analyzing a fuel cell at STP. So if we look at water as a liquid, water could be a gas. So At over 100 C, it's definitely going to be a gas. At lower temperatures, it's more likely to be a liquid, but that's not to say that it can't be a gas at lower temperatures. H2 and O2, just especially considering you're kind of forming it in air. So, and then we're going to have our Gibbs free energy of, or sorry, our enthalpy of formation in kilojoules per mole. We're going to have our entropy in kilojoules per mole Kelvin. And so we have negative 286, negative 242. And when things are in their elemental form, just, their lone element in their most stable form, that's usually the reference as 0. So then we have 0.07, 0.188, 0.131, 0.205. So the one other aspect of this, so I'm gonna kind of give you some of these values. So we're gonna, in here, what we're gonna want to work to do is calculate V at uh, at H2O being liquid and gas. So we'll do that, and then we're gonna go into a practice just now into, well, let's compare what happens when we try and just use these values at different temperatures to solve for it versus when we actually have tabulated data for different temperatures. So that'll be, and so prop 2, so let's come to our prop 1. Prop 2, we're gonna have temperature in Celsius. We're gonna have delta G, and so this will be 25, 80, 100, 200, 400, 600, 800, 1000. This is negative 237, negative 228, and these are in kilojoules per mole. And this is the case where these are liquid, and then the rest are gas. So you have negative 225, negative 220, negative 210, negative 200, negative 189, negative 177. So next we're gonna try and calculate the voltage for using any temp between 25 and 100 C, 1000 C. All right, so I'm gonna end this video now, and then I'm gonna make another video here in a short bit about kind of doing the program, introduction to doing a little bit of programming here in MATLAB for these different problems. All right. Thanks everyone. I'll see you in the next electrochemistry section.